Welcome to the second of this series of presentations on drill string and drilling dynamics. My name is Ben Jeffryes. I'm now retired, but before then I was a scientific advisor with Schlumberger. This one is on rotational dynamics, and it's a big topic. It's so big that my first attempt at recording a video on this exceeded YouTube's maximum file size, so I've split it into two. The first presentation was on axial dynamics, and now we move on to rotational dynamics, which is a much larger topic. I'm not even going to be able to fit it all into this pair of presentations. I'm not going to be able to include the whole subject of high-frequency oscillations, which are covered in Part 3 for oscillations during rotary drilling and Part 5 for oscillations below a motor. In this first half, I shall introduce rotational waves and show you what they look like, and then talk about how the bit both generates and amplifies rotational waves. In the second half, the other topics will be covered, such as friction and attenuation, low-frequency stick-slip, start-up oscillations, and BHA resonances. High-frequency oscillations will have to wait until I've told you about the effects of periodicity and positive displacement motors. First, I'm going to show you what rotational oscillations consist of, after a short recap. Remember, from the first presentation, while axial and fluid waves have a damping boundary condition at the bit, rotational oscillations don't, which means that a lumped parameter, long time model, doesn't work well. Now, at this point, I would really like to show you some real data. These presentations are based on ones that I prepared after retirement for Schlumberger's training arm, Next, to be given to an unrestricted audience, internal and external to the company. They included data recorded using Schlumberger tools. I asked for permission to show that data in these presentations, and they refused, even for data that had already been published and can be reached in a few clicks. So I've synthesized images that look very similar to the real thing. If you want to compare them to the real thing, this is where you can find most of it. Search for the proceedings of this colloquium and the paper on the right. Here's a recreation of 800 seconds of rotation speed data, measured near the bit using a gyroscope, and it's based on figure 1 from the paper. It's fast rotary drilling. The mean rotation speed is 210 RPM, which is higher than usual, but while there is a lot of variation in the bit speed, it's never close to stopping. I think it's obvious to the eye that there is something periodic happening here. This is the low-frequency part of the spectrum of that data. The y-axis is logarithmic, so the data is actually dominated by the first 3 peaks, which are all below 1 Hz, and are the regular spiky structure you saw in the time domain in the previous slide. Interestingly, the biggest peak here is not the lowest mode but the second one. Although they are not so big, there are well over 20 resonances clearly visible in a very regular structure. Theoretically, the lowest resonance is close to a quarter wavelength resonance for rotational waves, and the higher ones multiples of half a wavelength greater. So the second is at 3/4 of a wavelength, third at 5/4, etc. And by eye, this is borne out by the data. There's a secondary periodic structure here, with an enhanced response to about 3.5 Hz and multiples, and this probably comes from the drillstring structure. There is heavyweight pipe above the bit and the BHA. Remember, this data is measured in the BHA, and there is a large impedance contrast at the top of the heavyweight. So if a multiple of half a wavelength of the vibration is close to this length, there is an enhanced resonance. I say probably, because while going through this, I realized that 3.5 Hz is pretty close to the average rotation speed of the drill string. So it could be that this broad peak actually reflects the varying rotation speed. I don't think it is, because if it were, the peak at nearly 7 Hz would be twice as wide. Now, of course, my synthetic spectrum might just be wrong, but if you look at the real data in the paper, it's not twice as broad. This is the same data, now going out to 100 Hz. It's quite resonant out to 20 Hz, but then the resonances merge into a more general background. The higher frequency periodic structure, with a periodicity of about 20 Hz, comes from the impedance contrast at the top of the collars in the BHA. It looks like it's all going to be pretty boring now, out to Nyquist. But going out to the maximum bandwidth of the gyroscope, suddenly some really sharp resonances appear, at around 140 to 170 Hz and 280 to 350 Hz. In the actual data, the resonances above 250 Hz do not appear so large, but that is because the anti-alias filters started having an effect above 200 Hz, so I have attempted to remove their effect in this simulated data. I think it's clear that rotational oscillations are complicated. Remember, all this is perfectly normal drilling, a variation in drilling speed about 30% of the mean, so nothing abnormal happening, certainly no stick slip. In fact, during drilling, near-bit rotation speed often looks a lot like this, full amplitude oscillations. This is synthetic, but it's based on data from a near-vertical well. The rotation speed is oscillating between 0 and twice the mean, in this example at the fundamental resonance of the drill string. The drill string doesn't stop at the bottom of the cycle, or if it does, not for long. You may think that somehow the bit stopping is driving this behaviour, except, while this example is for rotary drilling, you will see this just as much during motor drilling, with the motor rotating nicely at near constant speed. The drill bit is rotating at the sum of the drill string rotation speed and the motor rotation speed. So the drill bit is always rotating at a good speed, but the drill string speed is oscillating between 0 and twice the mean. But that isn't what always happens. This synthetic graph is based on low-pass filtered data and just shows the low frequencies. You can see that there are two dominant frequencies, which are the bottom two harmonics, one approximately 1/4 wavelength and the other approximately 3/4 wavelength. Because the drill string has a BHA and other structure, the second resonance is not at exactly 3 times the first resonance, which is why you see this interesting peak frequency modulation. This is another illustration of why this stick slip cannot just be coming from bit excitation. This is the kind of behaviour often seen running into hull for a horizontal well, again of course synthetic data. This is one stand, 30 metres of pipe, going into the well while rotating. At around this depth in the data this image is based on, every stand looks pretty much like this. This was at about 7,000 feet. Same well at 17,000 feet. It's getting a bit odd now. Sometimes smooth rotation, other times sticking a lot. You can see the flat patches where there is no rotation. During this, the top of the drill string is rotating at a constant 90 or so RPM. Maybe things just get odd and sticky as you get deeper and there is more borehole drill string contact. That's not what happens. From this point on, the oscillations are much lower and the bit reaches bottom with only a small amount of rotational oscillation. Just quoting numbers, it is easy to forget quite what is happening here. We have over 5 kilometres of thin pipe, less than 15 centimetres wide, lying largely on the side of a horizontal borehole, being rotated from one end. It's quite remarkable that there is anything close to smooth rotation happening at all. To understand all this, we're going to have to get into some maths. To recap, remember this conceptual model. Things happen at the bit, things happen at surface, and the drill string conducts waves from one end to the other. At the bottom end of the drill string, we have the bit, and I'm going to be looking at what happens with PDC bits. There is a drawing of one on the right. PDC stands for polycrystalline diamond compact, and it is the material that faces the cutters, and it is incredibly durable. These are drag bits, the cutters simply rotating around, removing the rock that is in their way. As the rock is not a uniform material, this generates vibration, so you would expect to see vibration at the rotation speed and its multiples. But in the spectra I showed you, this is not visible. However, if you plot the data correctly, it is. If, instead of using clock time, you use cumulative angle, then the data spectrum is dominated by harmonics. But in the normal time spectrum, because the rotation speed varies so much, the harmonics wash out, and the only visible structure comes from the drill string resonances. In what follows, I'm going to be concentrating on the other effect of the PDC bit, which is as an amplifier, amplifying any rotation speed variation that comes down the drill string. What describes the waves going up and down is a pair of simple equations that link the time derivative and the spatial gradient of a local stress and a local velocity. It's the same equation for axial waves, acoustic waves, and rotational waves, just different variables. For rotational waves, the stress term is the torque, the velocity term is the rotation speed. The drill string structure appears in the matrix on the right-hand side. The density and shear modulus of the steel, and the geometric moment of inertia per unit length of the drill string. The F term is for any external rotational distributed torque being applied, such as the torque variations from the bit cutting process. Solutions to this equation can be described in a very simple way, as waves either going forwards or backwards, with a constant ratio of the torque to the velocity, the sign depending on which direction they are going in. Let's look at a very simple model of a drill bit on the end of constant cross-section pipe. Waves go up and down the pipe and interact with the drill bit. Most of these waves will have been generated by the drill bit. We have seen from the resonance structure of the spectrum that they go backwards and forwards many times between the bit and the surface or other reflectors. As I said, the motion in the pipe consists of forward and backward going waves, so subscripts F and B. The ratio of the torque to the rotation speed is the rotational impedance, Z, with the sign depending on the wave direction. The waves go forward to the bit, hit the bit, and then the reflected wave goes backwards. Now the bit boundary condition actually couples axial and rotational waves, so a wave of one type, going forward and hitting the bit, will be reflected into both rotational and axial waves. So we also need to decompose the axial velocity into forward and backward components, and the corresponding stress term is the weight, and the proportionality is the axial impedance. The boundary condition we are going to apply is the PDC bit condition, which is that the torque and weight are both proportional to the depth of cut, i.e. the axial velocity divided by the rotational velocity. In the two equations on the lower left, I have multiplied through by the rotational velocity. There are two constants here that are properties of the rock and bit, E and S. Loosely speaking, for the same bit, the harder the rock, the higher E and S are. E over S has dimensions of distance and is clearly related to the bit radius. So E divided by S times the bit radius is dimensionless. For a normal, sharp PDC bit, this is typically less than 1, and is fairly constant for the same rock type. As the bit dulls, it will increase, as there is more frictional drag on the drill bit. This model is a simplification of Emmanuel de Turnay's model, ignoring the much less efficient cutting at very small depth of cut, which is reasonable once the drilling process is underway. If you look at the torque equation, you can see that the left-hand side is the mechanical power being exerted by the drill bit, and the right-hand side is proportional to the rate of penetration, i.e. the rate of rock removal. So what this implies is that in this model, the energy required to remove the rock is independent of rotation speed. This is a good model at the weight and torque levels normally used. Remember that for this model to apply, the rotation speed has to be positive and the rate of penetration has to be positive. This is a model of a bit cutting rock. The bit here is a boundary condition, and what you look for at a boundary are reflections. Given what is coming down the pipe, the forward components, what do you get back? The reflected components. So I'm trying to solve for the reflected components, omega b and vb, in terms of the incident components, omega f and vf. From the weight equation, we can write the weight and velocity in terms of the forward and backward velocities, and substitute for the reflected velocity vb in terms of the incident velocity vf. Putting that into the torque equation gives the bottom equation. What does this show us immediately? Firstly, the reflected axial velocity vb is smaller in size than the incident axial velocity. Since omega, the rotation speed, is positive, s minus I omega has to be smaller in absolute size than s plus I omega. Secondly, looking at the rearranged bottom equation, the reflected rotational wave has to be smaller than the incident one. Omega f minus omega b is a positive term. This is good. Waves go down the pipe, they move the bit around and forward, and smaller waves are reflected back, so work has been done in cutting rock. So why did I say that the bit acts as an amplifier? One of the equations is nonlinear. Let's look at what happens when the system is in steady state and there is a small disturbance. So I am linearizing around a steady condition with a mean rotation speed and a mean depth of cut. Not the depth of cut per revolution, but the depth of cut per radian. There is one term multiply the rotation speed. Remember, this is the small varying rotation speed on top of a mean term, and another multiply the torque. Dividing through by the constant E, the rotation speed term is multiplied by the mean depth of cut, and the torque term by a constant I am calling epsilon, that includes the mean rotation speed. The linear equation is simply that the torque is proportional to the weight, and I am calling the ratio of constants E and S gamma. This has units of distance, and is typically proportional to the bit size. Now we have two linear relationships between the reflected components with the B suffix and the incident components with the F suffix, so we can write the reflected components in terms of the incident components, which is what you see at the bottom. The diagonal elements are not much different to 1 and -1, implying near total reflection. But let's look at them in turn. First, the rotation reflection coefficient. The most important fact about this is that it is always greater than 1. I've approximated the denominator here as z, but if you look at the full expression with no approximations, this is also always greater than 1. Let's look at the different terms in the amplification. It is proportional to the depth of cut, which is proportional to the mean weight and torque. Basically, the harder you push the bit, the more the amplification, and also the faster you're drilling, the more the amplification. The ratio is dimensionless. On the top is depth of cut. Z over I is proportional to tubular radius squared. Gamma is proportional to bit radius. So for the same depth of cut, it is larger for smaller holes. Also, there is a bit radius on the top and tubular radius on the bottom. So for the same size tubulars, it is larger for larger bits. But there is a conundrum here. Where is this energy coming from? We saw from the full equations that the reflected wave is smaller than the incident, but this analysis shows amplification. It seems like a contradiction. The answer is actually quite simple. Here is a solution to the full nonlinear equations, with an incident wave of average amplitude 1 and about 10% oscillation. The reflected wave, in red, is clearly smaller. Cutting rock is using rotational energy from the drill string. However, looking at the right, you can see that the variation in the reflected wave is larger than the variation in the incident wave. The amplification of variations derives from converting steady-state rotational energy into more variation. What about the axial reflection? Firstly, the sign is negative, but the amplitude is also close to 1. But it looks like it can be either greater than 1 or less than 1. So it can apparently either amplify or attenuate the incident wave. However, looking in more detail, whether it is more or less than 1 depends on the difference between the mean torque and z times the mean rotation speed. And if we go back to the equations that relate axial to rotational velocities, we find that for the reflection to be amplifying, the axial velocity has to go negative, in which case the bit boundary condition does not apply, as the bit has come off bottom. So maybe there cannot be axial amplification. Let's see. The normal kind of case is shown here, again with an incident wave with 10% variation. Blue and black show the incident and reflected axial waves, opposite signs of course, and in green is the sum of the two, the total axial velocity. I'm also showing the rotation speed in cyan. By eye, the variation in reflected axial velocity looks lower than in the incident, and that's what you see on the right. Less reflected axial variation than incident variation. So is it actually possible for there to be axial amplification? The answer is yes. We've been looking at a linear approximation to the bit reflection coefficient, but the actual equations are quadratic, and sometimes they have no solution. That means the bit won't cut. This corresponds to putting too much weight on bit for the available torque. That kind of situation is shown in the graph on the left. The reflected axial wave is very similar in amplitude to the incident wave. And with the axial wave cycling up and down, the bit stops once per cycle when the axial load is too high and the restarts when it's lower. If we look at the variation in axial velocity on the right, you can see that the axial wave variation in the reflected wave is larger than the incident. This example is difficult to convert to real life, as what we are looking at here is a drill bit on the end of an infinite drill string. In a real system, the reflected rotational wave goes back up to the surface, and the top drive controller increases the torque to keep the rotation speed up. But there will be a delay before this happens, so it is quite possible for axial waves to be amplified for brief periods. In the third presentation, I shall show some bit bouncing, which may have been in part from this effect. We shall also see in the fifth presentation that if a motor is added to the system, axial wave amplification does not require the bit stopping, but can occur in other circumstances. I showed you that the bit equations are quadratic. One way of writing them is shown here, with the total resulting bit rotation speed written in terms of the incident rotational wave, omega f, and the incident axial wave, Vf. I've written it like this, as it shows that any solution with a positive rotation speed, i.e. a physical solution, lies between 0 and twice the incident wave rotational speed. Obviously, multiplying through by the denominator on the right gives a quadratic equation for omega, the total bit rotation speed. We know that quadratic equations either have two real solutions or none. If there are no solutions, it implies that with these parameters the bit will not rotate. If everything is kept constant except Vf and Vf is increased, for some value of Vf there will be no solutions. This corresponds to the weight being increased quickly and stopping the bit. Normally, there are two mathematical solutions, but only one physical one. The other mathematical solution has a negative bit speed, and this positive solution must be the speed that the bit rotates. But what about when there are two physical solutions? This has to occur sometimes. If the Vf term is increased, going from one positive solution to no solutions, at some point when the Vf term is close to there being no solutions, the two solutions must be very close together, so there will be two positive solutions. So what speed does the drill bit rotate at, the larger or the smaller solution? I came up with this analysis many years ago, and it was a long time before I realised the answer, which is actually quite simple. We need to put in some dynamics, and we do this by adding some moment of inertia, J, to the bit. The torque equation now includes the change in bit inertia. We can now rearrange everything to write the bit rotational acceleration in terms of the two roots to the quadratic equation, omega r plus and omega r minus. Think of the situation where the bit is drilling along nicely, and then the rock type changes, so S and E have changed, and now the bit has to transition to a different rotation speed. If there are no solutions to the quadratic equation, the right-hand side is always negative, so whatever the initial rotation speed of the bit, it stops. If there is one positive solution, if the initial rotation speed is greater than this, the bit slows. If it is smaller, the bit accelerates, so the solution is stable, the bit speed moves to this solution. If there are two positive solutions again, if the initial speed is greater than the larger solution, the speed declines. And if it is between the two solutions, then it increases, so the upper solution is stable. However, if it is below the lower solution, the speed decreases again, reducing to 0. So the upper solution is stable, the lower one unstable. If the initial speed is between the two, then it accelerates to the upper solution. If it is below the lower solution, then it slows to a halt. So as Vf increases and the quadratic gets closer and closer to having no solutions, the range of speeds for which the bit will speed up to the upper solution gets smaller and smaller, until when there are no solutions the bit stops for all initial speeds. Time for a pause. That last section had quite a lot to take in, and you might need to go through it again. The most important part though is quite simple. The bit acts as a generator and an amplifier for rotational disturbances. What goes down the drill string and hits the bit comes back bigger. So if there isn't any attenuation elsewhere, or the attenuation is less than the amplification, resonances will grow. The other main point is to remember that the bit boundary condition couples axial and rotational waves. This is not surprising. More weight on bit means more torque is required, and the bit slows down. Higher rotation speed means higher rate of penetration. That's the end of the first half, to be continued in part 2b.